Hey everyone, so my name's Solomon. I'm the founder and CTO of .cloud, and I'm going to talk about Docker. All right, so suspecting that I would be talking to an audience of mostly technical and expert people, I looked for the shortest slide deck I had, and what I'm hoping to do is dive into demos, if you guys are down for demos. And then as soon as possible, since I know at least some of you have been playing with Docker and are thinking about different ways of using it, hopefully we can go into questions and we can steer this in the direction that you guys want. So first things first, Docker is an open source project. It's a project that we released at .cloud a few months ago. And by the way, .cloud is a platform as a service. So we deploy and host and manage applications for developers who don't want to spend the time and the money in managing the infrastructure themselves. So if you guys know about Heroku, then .cloud is a competitor of Heroku. And so we've open sourced Docker, which is really at the core of a lot of the technology at .cloud. And it started as a side project and then surprised us, basically, by becoming pretty much the most successful thing we've ever done. And these numbers are completely out of date, by the way. I think now we're more around 160 contributors. I think we're just reaching 6,000 GitHub stars, and the project is basically it's 5 months old, right? So imagine put yourself in my shoes. We're putting out this side project, seeing if people are interested, and then a few months later, 160 people actually contributed code into it. So we've had to organize pretty seriously to deal with that unexpected popularity, and obviously it's a very good problem to have. So I'm going to talk a little bit about why this is so exciting. By the way, this is the ego slide. A lot of engineers are playing with it, experimenting with it, and although it's not production ready, some people on this slide may or may not be ignoring our advice to not use it in production yet. So it's popular, and so the typical question I get is, why is it so popular? What's the big deal? Especially if you know about the underlying technology, you might be wondering, well, I knew about containers, so what's changed? So the high-level story here, the reason I think it's popular is that basically shipping code to a server is really hard. It should not be hard. We have become experts at working around that difficulty as a profession, but really it shouldn't be that hard. It shouldn't take that much expertise, right? Especially if you compare it to getting code into a mobile device. The level of tooling that is available to everyone out of the box is just still needs a lot of work, let's put it that way. And so you guys know all this, but also I'll keep it short. But once upon a time, the typical stack looked like this: the server, the framework, the stack, and that was it, right? The server with a capital S. And now it looks more like this, right? You've got a software stack that is much more distributed and complex and diverse. It's service-oriented. It's loosely coupled components, different languages, different frameworks that might change over time. And that software stack needs to run on a hardware infrastructure that itself is becoming larger and more complex and more diverse, right? It starts with your laptop, your colleague's laptop, the test machine, QA, your in-house cluster, the public cloud cluster, cross-cloud deployment. Increasingly, you've got software companies that offer a SaaS service, and then their customers say, hey, I would like an appliance of that, right? Can you ship that as an appliance? By the way, I run this or that infrastructure setup. And so you have a more complex software stack that needs to run on a more complex and diverse hardware infrastructure. And the result is what I call the matrix from hell, or the matrix of doom, which if you're in the profession of writing or shipping software, you're familiar with it in one way or the other. You've got every software component in your stack multiplied by every place where it might need to run one day. And your job is basically to make sure that every intersection of that matrix somehow works, right? Tests pass in the same way on every intersection. If the tests pass on my laptop, then hopefully the tests pass in production, and dealing with those possible differences, right? So the typical scenario where that doesn't happen is where you're developing on your laptop, and it's a certain version of Python, a certain version of the libc. It's a certain distribution, and then it works on your machine, and then you ship it to production, and it's not Ubuntu, it's Red Hat or CentOS, right? It's not Python 3, it's Python 2.6, et cetera, multiplied by all these different rows and columns. So in a nutshell, what we're trying to do with Docker is contribute to solving this problem. And one way you can think about the problem and look for possible solutions is finding a group of people who've had that problem in the past and solved it, right? So the analogy we like to use is the shipping industry. If you need to ship stuff somewhere in the world, for centuries the problem was basically, well, I need to ship coffee beans. I need to get them on the other side of the world. It is my problem how those goods are handled every step of the way, right? What kind of truck is going to be used? Is the staff trained to handle those kinds of bags in Rotterdam, et cetera, et cetera? And so the process of shipping my stuff is very tightly coupled to my stuff, right? Which means that every single provider of goods has to have an expert in-house and has to map out routes and think about plan B and have all that knowledge and infrastructure in-house. And so it makes for a very brittle and expensive and unreliable process. And of course, you can represent that by the same matrix from hell, right? Every possible goods to ship multiplied by every possible way to ship goods. Same problem, except they solved it, right? They came up with this. They came up with the shipping container. They all agreed on a box. They agreed on the size, the weight, the dimensions, all the dimensions, how the doors worked, where the locks are, where the ID label is, and then infrastructure providers standardize on that, and people shipping goods standardize on that too. And so now all of a sudden you get separation of concerns, right? I'm shipping coffee beans. Now my problem is simply to load my goods into this box, seal it, and once it's sealed, it's no longer my problem. I can hand it to a wide variety of infrastructure providers. I can organize in such a way that later new infrastructure providers or new infrastructure tools can be added. I don't have to repackage my coffee beans just because we're not going to go through Rotterdam anymore. And conversely, if I'm developing infrastructure, right, I'm managing shipping routes or I'm building trucks or boats, I can standardize on that and focus on a differentiation, right? Faster boats, cheaper, better organized facilities, et cetera. So separation of concerns brought efficiency, automation, and really that changed the world economy, right? Because it's so much cheaper and more reliable to ship things. We could probably point to 15 examples in this room of things that wouldn't exist or things we wouldn't be wearing or using if the shipping container didn't exist. So the goal really is to try and do the same thing for software, right? Because I think it's embarrassing, personally, that on average, it'll take more time and energy to get a distributed system, a collection of software to move from one data center to the next than it is to ship physical goods from one side of the planet to the other. I think we can do better than that collectively. It's software, right? So that's what we're trying to do or contribute to. And the way we're doing it is we're trying to define a standard format that is simple enough and sturdy enough that a critical mass of people can agree to use it and integrate with it. And so really the metaphor is that, if you're a developer, those are the goods, or that's the software, the bits are there. Docker gives you a standard way to pack that into a box with standard properties, and then you can hand that box to tool makers, ops teams, infrastructure providers, and they know how to handle the box, and they will handle the box in their own particular way while you know exactly what's going to happen in the end, right? You know how things are organized inside. So the developer worries about inside the box, infrastructure worries about outside the box, and then things are interoperable, repeatable, and ultimately they're cheaper and more reliable. So that's the goal. That's the most high-level possible thing I could have told you. That's what I just said. And that's the end of my slide deck. So I told you virtually nothing in terms of how we do it or why you should use it. But that's the goal. I think it's a good idea to start with that. So before I dive into technical details, demo, do you guys have any questions? The question is, isn't there such a box format already? And actually, don't we have already too many of them? Is this the case of creating the 15th standard to fix the 14 previous standards? Okay, so you don't read Hacker News, but you read XKCD. I get it. Yeah, so the starting point of all this, is that we as a team did not kind of set out to create a standard for the sake of creating a standard. As a starting point to answering your question, as a provider of a hosted service, right, a platform as a service, where our job was to run and deploy web applications, API endpoints, databases. The value proposition of .cloud was we can run a lot of things for you, not just the Rails app, but a lot of components of the stack. So we were faced with this problem of, if we were going to run a lot of different kinds of things for a lot of different people, for a lot of different developers, let's see what's available that we can tell them, hey, package it in this way, and then we'll run it. And so VMs are definitely an option. I would say they're on one side of the spectrum, right? And then on the other side of the spectrum, you have VMs being the least application-specific thing. They're kind of lower in the stack because you're basically shipping an entire machine, virtualized machine, but still a machine. And on the other end, you're shipping a static binary, or maybe you're shipping a jar if it's a Java application, or a Python package, or maybe a system package. And then you have something that's much more lightweight. You need to send less bits because really there's more context, right? If I send you a jar, it's implicit that you already know I'm going to send you a Java application. So normally, I would expect that you have some sort of Java deployment environment already in place, and I'm only shipping to you the missing parts, right? The problem is the part that I'm not shipping has to be this, I have to know for sure it's going to be there. And the problem is when I'm sending a jar, I don't know for sure what's going to be there. And a larger problem is that increasingly, because of this distributed, complex, diverse software stack, it's increasingly unlikely that the entirety of my stack will be Java, right? Or will be Python. And even if it's Java, I might want to rely on a specific version of Tomcat or a specific version of the JVM, et cetera. And so how do I, the developer, make sure that it's that version of the JVM that's going to be used and not another, for example? So if I want to do that, if I want to ship everything around the application, right, all the way down to what version of the application server, what build, what exact configuration, an exact build of the libc of everything, then the only option that's left to me is a VM. So the VM is the only existing format today that will let you ship enough of the information you need to ship as a developer. And the problem with VMs is that they ship too much, right? You're shipping a whole machine, and that causes multiple problems. One is that it's a lot of bits. You're sending files that are very large. It's also a lot of overheads in deploying them. And the overhead manifests itself both at the very low scale, small scale, and large scale, right? If I'm going to do integration tests of a stack of 10 components on my laptop, that means I might, if I'm using VMs as the unit of delivery, then that means I have to deploy 10 VMs. And 10 VMs on this laptop will definitely not take 10 VMs. So there's the problem of just performance and overhead. And then the other end of the spectrum, when you've got massive scale-out deployments like you guys have, where a given payload may need the entirety of a machine, the overhead of a VM might actually not be worth it either, because would you rather buy 20% more machines or get rid of a 20% overhead, right? So I'm only partially answering your question, but really the point is there's a missing middle ground where the developer ships enough that he's specifying enough that he can guarantee this is the same thing that will run over there that I've tested here. So it ships enough, but it doesn't ship so much that now he's telling the ops team how to do their job, right? Here's how storage should happen. Here's how much RAM this will have. This is a virtual Ethernet interface. NATs is in place. These are ops decisions, right? So it should be possible to ship the same application bundle, to run the same application bundle once on an SSD array, once on a clustered file system, and once on just shitty local storage because you're just testing, without having to rebuild the application 3 times. Does that make sense? So that's kind of the problem, right? The reason the tools existing today don't solve the problem in a way that's really satisfying, and then at the same time, new tools are now possible because Linux just got a hell of a lot better, and now it's capable of cleanly sandboxing the execution of processes. So with the namespace and control groups features, the set of features commonly known as containers, now it's possible to basically, the low-level primitives are in place in the Linux kernel by default to basically execute processes in a way similar to the way they're executed on an Android device or an iPhone, for example. So it's possible for me to drop into a server a set of files and execute a process in that directory in a way that is completely sandboxed from other processes. And that is really nice because now I can have this really clean primitive for deployment. I can install an app without worrying about how it interferes with other apps that are installed. I don't have to worry about conflicting dependencies, 2 different versions of the app requiring 2 conflicting versions of a given library. The library will just be installed twice, once in each container, right? And it's only, that development is fairly recent, right? At .cloud, for example, we've been using containers for a while. A lot of people have, but the problem is that you had to build your own custom container-based system, if only because it required patching the kernel, which just, that's it. You can't have a critical mass of people using containers to share and reuse software components because most machines out there can't run containers, right? So now they can, which means we can now define a new unit of software delivery that's more lightweight than a VM, but can ship more than just the application-specific piece. So Docker is a rewrite of the system we use in .cloud. So it's not the actual same code. And people ask us, when will you say it's ready for production? Roughly speaking, we'll tell other people they can use it in production when we're comfortable using it in production. Which the progress towards that is fairly rapid because we know the design. It's very similar to the stuff we do run in production today. It is a rewrite. And the reason it's a rewrite is Docker does much less. .cloud is a platform, right? It does everything for the developer using it, from setting up resource allocation strategies across clusters of machines to load balancing to all that stuff. Docker does less. It's a more concise tool. And one of the key design principles behind Docker is that it should be possible to use it as an ingredient in your existing platform. For example, one of the conversations that's going on in the Docker community is, Mesos is really cool. Maybe we could use Docker as an ingredient for Mesos deployments, right? Conversely, we want to use Docker as an ingredient for .cloud. But in order for that, that's just the way, I guess, system design works. If you start a component, Docker's grandpa, it's too late for Docker's grandpa to be ripped out. It's .cloud specific. But through a rewrite, we can have a reusable version. One of the concrete applications of making Docker an ingredient is we've tried to make it as easy as possible to drop in, like as actually physically drop into a system. So Docker is a static binary that you download onto a server and execute. First, you run it as a daemon. And once the daemon is running, you can run the client. You can just type commands, and it will pass commands to the Docker daemon, and you're in business. So right now, this is a VM running on my laptop with the Docker daemon running in the background, so I can start typing Docker commands. So the first thing I'm going to type is Docker PS. So notice PS is reminiscent of PS listing processes. Docker has a process-oriented API, and that is one important distinction with existing container tools. You can use Linux containers without Docker, right? We did not invent process isolation or Linux containers, but a lot of the tools out there will focus on using containers as basically miniature servers, right? You set up a file system, you boot it, and it's just like a VM, but it's way faster. What we're interested in is using containers, again, as a unit of software delivery, so really an envelope for running an application, which means that a lot of the commands and API calls are process-oriented. So here I'm basically asking, hey, what processes are running in their respective containers? Nothing is running, so I can Docker run something, and in order to run, I need something to run. So we have a concept of images, which is basically file system states, basically tarballs that you can start from, and then you execute processes inside those images. So this is what I meant by readable characters or readable lines. Choose one. Let me try and find a good trade-off here. Oh, this is nice. Is this still readable? OK, so a lot of output here, but basically it's a list of images. On the left side, you see names. And so this is my dev machine, so I have a bunch of stuff lying around. What I have here is an Ubuntu image. So if I filter it down, I have a few images called Ubuntu, and they have tags to indicate versions. So here you can see I have a base system, a base Ubuntu 12.04 system, a base 12.10 system. So let's use that. So I'm telling Docker, hey, run a process inside the Ubuntu image. Let's say 12.10. And the process I want you to run is bin bash, right? And then I'm just going to add a flag to say, hey, I would like to attach to the input of this process so I can type things in, and get, in addition to having things printed. And that's -I for input, and -T is, and also I would like you to allocate a TTY so that things look pretty. So if I do that, it's going to create a new container. And so this is a shell in a brand new container. So Docker just created a copy of the base Ubuntu file system, set it up, you created a Linux container in there, set up networking so I would have a network interface, give me an IP, and then executed the process I asked for in there, sandboxed, and then attached to it so I can see the inputs and outputs. So notice that all of this happens pretty quickly, so I can do it a bunch of times. Every time I do this, I'm creating a new container and then executing a process in it. Yep.
Can it also run in it?
Sorry? You can run in it. Yeah.
You can, or does it?
Oh yeah. Right now, what I'm doing here does not run in it. So it's literally, well, actually, here I'm in a container, right? If I look at all the processes running, this is all there is. There's only bash and PS, which I just ran. That's containers, right? My shell is completely isolated and it has a full file system all to itself. And the cool thing is it's a copy, so it's not sharing it with anyone else, right? That's the key primitive. Every time, basically, the fork primitive that we all know, when you execute in a process, you fork the process. Now you also fork the file system that is sandboxing the process at the same time. So what that means is now I can do whatever I want in this file system. So a few times ago when I gave this demo, someone said, prove it. And so it made me remove all the file system, which is always a little traumatizing. So I'm just going to remove var and etc. Yeah, OK, I'm in the container. Yeah, so I'll go into the resolve.conf thing in a second, but I did remove var. OK. OK, so I removed bin. So I'm screwed now. But that's OK, because I can exit, and then run a new container, and then it's back, right? Because it's a new copy. So you get this. The first thing you get out of this is you get a really easy way to throw away a setup and just start a new one, and you know exactly what your starting point is, right? So that is a really nice, solid foundation for a lot of things on top of that, right? Whether it's configuration, installing applications, build, etc. You always have a safe place to go back to. And the other way today, the alternative to that today, is setting up a VM and then snapshotting the VM and reverting to the state of that VM, which may or may not be practical. I definitely know I don't want to snapshot my VM every time I want to go back. It's just too slow, too cumbersome. I just do this. So yeah, that's changes to the file system. The other thing I want to show you guys is, what do I want to show you? Oh yeah, snapshotting. So let's say I'll just start a new one, and then I guess I'll remove var again. I removed var. I gave a demo yesterday where I removed var, and it went well. So I'm just going to do that. Come on, let's be brave here. So let's say one day I'm definitely going to remove it in my host machine, and I'll be screwed. So let's say that is a change I actually want, right? Oh, awesome! I removed var. I want to reuse this. So I'm keeping this shell on the left, and here I'm just logging into my VM again. And then let's list what's going on here. So you can see here, if I run docker ps, remember it listed nothing. Now it shows that container running, right? Bash running started 46 seconds ago. The starting image is Ubuntu 12.10. This is a unique ID. Everything has a unique ID always. So you always know, OK, I'm running this and not something else, right? You can always track what's going on. Let's say I want to use this, right? I want to publish it, actually. So I'm going to say, OK, first, let's take a look at the changes. And so here it's going to tell me, oh, you've removed a bunch of stuff, you idiot. And by the way, it works also for, like if I add, oh, right. Yeah. OK, well, you get the idea. And so let's say I like this, and I want to, so if I like it, at any given time, I can say, OK, commit. And let's call it, I can optionally give it a name. Let's call it Solomon's Broken Ubuntu. And there's kind of just a convention of username / name. You don't have to follow it. So OK, it committed, it gave me a new ID. And now if I look at my images, if I look for broken, then there you go. You have a broken Ubuntu image. So now, if I want, I can just use it right away. So run, same thing. Let's run a shell in broken Ubuntu. And, oh, wait. Oh, right, I removed too much stuff. OK, of course I had to hit that one edge case. Yeah. So if you guys are interested in the technical details, ideally you could run Docker into just any tarball at all. There are a few dependencies. For example, the IP binary needs to be there because we use it to set up networking for the container. But there is a pull request to fix that. So anyway, you guys believe me, right? Actually, so let's say, OK, great. Let's say I want to publish that. So one of the reasons it's interesting to agree on a really simple, conventional way to do this is that then containers become portable. And so they go from being a cool way to do miniature servers to being a cool way to doing basically libraries with more stuff in them. So the whole point is to use containers as a reusable software component, except instead of binding into it at linking, you execute and interact with it that way or over the network. So let's say I want to share this beautiful piece of software I just designed. So there's a built-in registry system where you can Docker push, let's say I just want to push broken Ubuntu, and then assuming there's internet, it'll connect to a public registry where anyone can just upload stuff and download stuff from each other. So it's just going to upload that container, and then if I go to the Docker index, and I look for Broken Ubuntu. Broken Ubuntu. So if you guys just go to that right now, and assuming you have Docker installed, you can literally copy this command, docker pull sx broken Ubuntu, and it'll download it for you, and you'll have on your local deployment of Docker the exact same awesome configuration I just created, and you can run it. Well, you can not run it. And so that's the basic mechanics of sharing. So one thing that you might have noticed is the upload was pretty fast, even though this is a full copy of an Ubuntu file system. Which the basic Ubuntu image there is pretty, it's trimmed down, but it's still, at least 100 megs. It's 100 megs uncompressed, I think. So how come it uploaded in 5 seconds? The answer is that behind the scenes, Docker handles versioning. So every time you commit you kind of fork a new container, Docker tracks the history of that container, just like Git commits. And so when I did Docker push, I did something very analogous to Git push, where my local Docker and the remote registry figured out which parts, which versions were already available in the registry, and then skipped those, right? And so the only thing left to upload was really the diff that said remove these 3 directories, because out on a way, and that was it. So that's fast, and that's why things happen so fast. So we use that copy and write mechanism for a lot of things, right? To speed up execution, you have that really nice primitive, oh, let me just run a new copy. It's really fast. It saves disk space locally, and it also saves bandwidth when you transfer. So you can use that primitive for advanced use cases, right? So these primitives really are all you need to compose even the most complex software delivery pipelines, right? So for example, if I have a continuous integration setup, where every time there's a new Git commit that's pushed, maybe you have Jenkins or Bamboo or something like that, checks it out, builds it, and executes tests in it. Well, now, one thing I can do is, starting from the source code, create a new container, run the commands necessary to install the dependencies, upload the code into the container, compile. Then I have the resulting application container, and then I can run tests. And then let's say I want to ship that out to 100 servers. Then I can do that without actually sending the whole thing 100 times. I'm only sending the diff. So in a typical setup, you've got a really fat base of the base system, and then all the system packages you need, maybe a Puppet or Chef custom configuration on top of that, and then on top of that, application dependencies, and then on top of that, the application. So if you build that multiple times per hour, really the only thing you're going to ship multiple times per hour is that top layer with a new build of the application, which is much smaller. So Docker just kind of does that without, but you still get the semantics of just pushing that image, right? You don't have to worry about, oh, let me just rsync this, and then I'll create a symlink, and I'll reassemble it at arrival. Docker just does it. So do you guys have any questions? Yeah, okay. Yeah, so beyond starting a shell and experimenting, which is really fun and gratifying, pretty quickly the Docker user community has moved on to, okay, now let's use this as a building block for the real deal. And then pretty much right away you have this question of dependency between containers, right? Containers are perfect for deploying network services, right? So something that exposes a TCP port, and then you can connect to that port. You have this kind of nice unit of it's the actual representation of that service that is abstract to someone else. And then, so there's 2 parts. There's how do I expose TCP ports or just a network service as a container? And then part 2 is how do I consume other network services that I depend on, right? And so the first thing we did is, for the first part, exposing ports, there's a whole port, there's a whole networking part to Docker that's built in. So for example, I'll give you a quick example here. Let me exit this. Let's say I want to run netcat, right? Or, yeah, I guess netcat will do. So I think netcat is built in. I guess not. OK. here's what I'll do. I'm going to start a shell and then install netcat and then run it. The key thing here is I'm going to add a flag, which is -p, and then I'll give a port number like 8080. And then now I'm telling Docker this container is going to expose a TCP port at port 8080. Just a heads up, the application is going to listen on this port and expects that port to be available for discovery, right? And so Docker out of the box honors that by sending up iptables rules. It'll choose a public port that's available on the host. It will set up DNAT so that the port's reachable. And then, so the container's running here. I guess I'll install netcat. And then here, if I look at the process, running, you'll see it says, it shows that extra information at the end, ports, right? And it shows, hey, port 49153 on the host is redirecting to port 8080 on the container, right? And by the way, just while I'm at it, this is a really cool use of diff. You can see what package managers do on the system. You can see what they put where. I use that to learn how things actually work. They install a lot of stuff is the short version. Anyway, so netcat is there, so I can listen on port 8080, right? Right. And so now let's say I'm an external, this is part 1, right? There's a container, it's exposing a port, and so now Docker makes it available for discovery. So these commands I'm typing to figure out the port to connect on, imagine instead there's some sort of service discovery system or orchestration that does the equivalent of this but with an API call and figures out, oh, this really cool netcat service is available at this address. And then normally here, right, maybe. OK, so I don't know why this doesn't work. OK, second try. All right, I guess, yeah. So I get an HTTP request coming in, and obviously it's not going to work, but discovery has enabled me to find the TCP port and connect to it. So that's kind of built in. So the idea is if you're the developer packaging the app into a container, that -p flag that I typed on the fly, you can also set default values into the container's metadata. It's just a very simple JSON file, and you can package it so that when I pull it, it actually already says, hey, I'm going to expose port 8080, and then I can just run it, and the port will be magically exposed. So that's like a key piece of information that the developer can pass on to the deployment platform by expressing exposed ports. And the second part is, OK, if I'm a container and I need to discover how to connect to some other external dependency, that's something that has generated a lot of discussion because there's a lot of different ways to do service discovery. And there are kind of subgroups within the Docker community using different systems to do that, including Zookeeper. And so initially the answer was, oh, let's just containers are there, and then they call out to your service discovery of choice, and then it's just like outside of Docker's responsibility completely. The only problem with that is that you need some sort of small indirection so that you can follow that kind of Unix philosophy of a component does one thing, it does it well, and then they can be composed in any way, right? Kind of like pipes. You don't know, a process doesn't know if its standard output is going to go to the standard input of another process through a pipe or into a file. It just knows it's printing out. And so we need the equivalent of that for linking to another service. So what we're adding in the next version of Docker, 07, which is coming out in 2-3 weeks, it's a monthly release schedule, is the concept of link, where you can link two containers. You can link one container to the other. And once a container is linked into another, it's available. That container can discover containers that are linked into it, and then it can inspect properties of that container, including the ports it exposes, and that can connect to that port. So for example, you would link the database container into the application container, and then the application container would introspect first the existence of that database container and then how to connect to it. The key is, how do you do something there that's thin enough that it doesn't conflict with using Zookeeper or another system. The goal is not to replace those systems, and Docker doesn't do, for example, anything on the wire. Like, it doesn't do any sort of distributed communication. It doesn't have a name service that multiple, a Docker host never talks to another Docker host. But the way we implement this is with a pattern we call the ambassador pattern. And basically we're saying there is huge benefit when you're architecting your stack if on any given machine, for example, your application container depends on an external service, for example, a database, it should not count on that service being on another machine or on the local machine, and that there shouldn't be no assumption there. So what we recommend is always, for each external resource that you depend on, always have a local representation of it as a container. So in other words, if on a given machine you're running an application container and it depends on a database, you should always have a database container there locally on the same machine. Whether or not that container actually is the database or it's just a placeholder for some remote database service, that now becomes an implementation detail. And that primitive, that notion of if I have a remote dependency, if I have any kind of dependency, it's going to be represented by a container locally. Now things become much simpler because the application container can now all it needs to do is use a very simple system to find that container and connect to it. Just look up, where should I connect to, and then connect. And then now you can swap out that dependency in all sorts of ways. Basically, you get dependency injection at every level of your stack. For example, you can run integration tests against your app and just replace the actual database service with a mock database that just parrots canned responses, but really is recording what the application queries to make sure the application behaves correctly. So now you can run full integration tests on a local machine with no internet connection. And for a good example is, a lot of applications obviously use the Twitter API, and they have this huge problem, which is, hey, my application stack now includes the Twitter API, right? And obviously the Twitter API doesn't run on my machines. It runs at Twitter. And sure, there's a mechanism for sandboxing, et cetera, but when I want to run repeatable offline integration tests, it's really hard to do dependency injection. I have to do it within each process. But if I have, say, a Node.js component and then a Ruby on Rails component, now I have to do everything twice, right? And if I want to, say, reconfigure my app to talk to a different Twitter account or things like that, then I have to change credentials everywhere. But with the ambassador pattern, what you do is you just have a container represent the Twitter service. And that container is maintained by the local development team. With integration tests, you have a fake Twitter account. For dev staging, you have a staging Twitter account. And then for production, you have a production Twitter account. Same thing for database. So that's how we address the problem of wiring containers together. And not going into the specifics of how discovery happens, but it becomes very simple, right? It's just there's a simple mode where we inject a few environment variables into the container, so you can introspect that. And there's a more advanced mode if you want to watch changes. If new containers are, you get new dependencies added dynamically, things like that. We expose as a tiny little Redis database that each container gets its own little Redis database with a live representation of what it can connect to. And then the idea is if you're deploying that in a massive Mesos-based cluster, for example, that would actually all be backed by Mesos service discovery. We've explored all the options. We've had like a prior alpha version that allowed for some merge mechanics, but really we just realized it wasn't worth it. At the end of the day, what kind of blurred things is that there's a lot of Git-like operations. So it's tempting to say, it's Git, right? So if Git does it, Docker should do it. But the key thing is a Docker container is not source. It's really more like a binary, right? And so you don't merge binaries usually, and you don't change them in place either when you're updating. It's more the typical process is more for a given checkout of the source code, I compile a binary, right? And so you have that one-to-one mapping. And so if there is a new version, regardless of whether it comes from a merge or just a change or anything, we've determined that the right approach in Docker world, at least, is to just rebuild the container from that checkout. But the trick is that the reason that's a viable option is because thanks to AUF, to the copy and write stuff and just the general implementation details, it's fast enough and cheap enough to rebuild that you can do it. Technically, you could rebuild a VM from every Git checkout. Nobody does it. I mean, some people do it, but it requires a lot of engineering, and it's cumbersome because building VMs takes forever, and it's not practical, right? The only company that I know that really does it beginning to end completely with everyone bought in is Netflix, right? And the result is they have standardized on EC2, and if you wanted even run an integration like a quick test on a given version of a branch or whatever, you have to actually spin up EC2 instances. So there's no merging. The other thing also is one scenario where it's tempting is when you say, well, I've built my application, it's all there. I just need to rebase it against this new version of the distro, right? But the problem is you can't, in practice, if you're going to install a package from a given existing system, that has side effects, right? You don't know for sure what apt-get install or rpm install does. It might just check for what's there. So we can't assume the result will be the same. So it's in some edge cases, it might be useful, but usually it's just better to assume, there's a better way. Thanks.